Yuri Elzur is a senior principal engineer at Intel's data center and AI group, where he leads GPU network architecture efforts. And prior to this, Yuri worked on network function virtualization projects such as OpenO and MANO, and ETSI's experiential networked intelligence specification group, the Open Daylight software-defined network platform, and many other prominent projects. And he was also a senior director at Broadcom, where he managed the networking and interface architecture team. We're really excited to have him here today because of one of his current roles, which is as chair of the technical advisory committee for the Ultra Ethernet project, which is in full swing. I think it just reached 0.75 or 0.8 or somewhere along there in terms of moving along towards a full specification. So he's here to tell us a bit about the challenges posed by AI and machine learning for scaling out communication and how Ultra Ethernet is going to target these challenges. So thank you very much.
Thank you very much. Can you hear me loud and clear?
Yep, and we can see your screen.
Perfect. So we'll change tempo a little bit. I'm honored to present here on behalf of a very large community, as you're going to see shortly. Obviously, the area of AI and the networking for AI is red hot. And without further ado, let me jump into this. Hopefully, we'll have time for questions at the end. As hopefully everybody can see, Ultra Ethernet Consortium, as you kindly mentioned, is at full swing. We did start with that group, as you see on the upper right side, that group of hyperscalers, system providers for both AI and HPC, as well as silicon providers for CPU, GPU, and network, all sorts of Ethernet, has actually created the consortium, but also had all the decades-long experience with hyperscale as well as with AI and HPC. We are blessed with pretty much the whole industry joining. Anyone who has anything to do with Ethernet technology has joined the consortium, and the consortium is alive and kicking, as you could see. The name always puzzles people. Oh, okay, so are you guys doing Ethernet, or what are you doing? Well, we did keep the name Ethernet in the title to send a very clear and strong message to everybody. This is based on your Ethernet, your familiar Ethernet. We have not changed anything. And if you could see at the bottom left, the four work groups that are listed as horizontal, those are the original work groups that we had in the consortium. True to our suggestion here, the physical layer allows us to work with existing Ethernet as well as supporting existing Ethernet switches. No changes required. Obviously, we'll discuss some optional features that are going to make your experience even better, but that is not required. So if you look at the top, from the software work group, we are supporting Leap Fabric API as one common example that is blessed by the whole industry. That also means that your application do not need to change. So we'll get back to those points later, but from frameworks, from MPI, from OpenSHMEM, you don't need to do anything. The key innovation that, or the bulk of our work happens to be around the transport. The consortium has renovated the transport services to better serve the needs of AI and HPC workloads. We have some additional features recommended also for the link, and we'll cover all of that. The other four work groups that are depicted here vertically simply show that we are ready to flip to the next page as our specs are about to be ready, and we want to move to compliance, to management, performance, and debug, which would be required for the products that we expect to see on the market soon. we also found a strong interest in storage over this new transport. And so that's the other work group that we have. All of those work groups are working also. The new ones are already working for quite some time. And the last comment about Ethernet in general, the key idea here is to keep the eventual standard. This is an international standard organization working under the Linux Foundation. The key idea is that the goal is to have a fully open as well as interoperable set of standards here, because there is a strong need from the industry as well as from customers to have those critical networks running on open, interoperable environment that allows the customers to choose products from many different vendors. Let me start by positioning our technology and the different networks that are involved in any kind of a little bit simplified, but still an AI node. What you see in the center, few accelerators, a few CPUs, and 3 different networks. They are really distinct in the nature, and each of them serving a little bit different goal. The very familiar data center network, network number 1, typically is running east-west as the bulk of the traffic, but also south, north-south with customer requests. It is a much larger scale for multiple reasons. It's going to have a little bit lower bandwidth per accelerator. And also the type of traffic that it services is typically bursty traffic, multiple application, each of them showing up at different time, which really makes it a little bit hard to control it in terms of perfect load balancing, high utilization, short congestion, and so on. The 2 specific networks that are being built for AI, very common in the industry, is network number 2 and network number 3. Network number 2, where Ultra Ethernet opted to start its journey, is what's called the scale-out network, typically serviced across PCI connection to an accelerator. Typically, the ratio was 1 NIC per accelerator. Much higher bandwidth, obviously, much larger scale, much tighter RTT, and definitely strong interest in congestion control, controlling the tail latency, and we'll talk about it some more. And then network number 3, the scale-up network. That network is the network that carries most of the traffic, as we are looking at a little bit of a waterfall in terms of bandwidth between 3 to 2 and 1. Started as a network that services accelerator on a single node, and recently is growing to a rack or more than that. So there were multiple reasons for Ultra. Oops, that is not good. That is always happening when the last thing you need here. I think it's gonna take a second here. Not sure why my machine is closing all the applications. So give me a second here to recover. You can still hear me, right?
Yes.
Okay, so I'll continue describing this while I'm trying to revive here that that machine. So we were discussing the scale up. Scale up is growing. There were multiple reasons, as I was describing, why we opted to start from the scale out, because on the data center network there wasn't really an opportunity to get an broad industry agreement, different players, different organizations are actually using different standards while all of this is Ethernet based. At the same time, the scale up was in many cases dedicated to a given accelerator, sometimes even to a different CPU, and so it was an easy decision to start from the scale out. Let's see if I can actually kick it off. I apologize, there are some activities that are pushed by my admin that I have no control over. Let me continue talking because I can get the slides from another source. Just a second. It's amazing that it cuts you in the middle of presentation. No ifs and buts. Okay, PowerPoint is reviving. Okay. Okay, looks like we'll be back in business in a second. Yeah. Everything should be back to normal at this point. Again, I apologize.
Yes.
Okay.
Screen is back. Great.
Yeah. Okay. So we were discussing the three different networks. Now let us talk about the two different key applications. As you could see on the left, and this is a little bit dated, but the message is still correct. AI applications, and in this particular example, it is a meta example, but yeah. But then you could see the different percentage-wise of time that the communication is exposed. One of the differences between AI network traffic and the whole computation cycle to the general data center was that AI is more systolic and therefore predicted. And so ideally, and in some cases, it's possible to hide the communication behind the computation. But in some cases, as the meta example shows, this is not possible. And therefore, there is high interest in optimizing the network with high utilization and low tail latency. On the right side, we can see HPC and HPC applications that are governed by MPI or OpenSHMEM or similar environments where ordered is controlled. Typically, they benchmark themselves by looking at the performance of very small messages, extremely latency sensitive, drop sensitive, require high cross bandwidth and so on and so forth. And that brings up a question of whether you could actually come up with one technology that can service both of them at the same time if they actually have different requirements. And the answer is, let us look at the different primitives that we need in order to support this seemingly different type of applications. In both cases, we need to service large scale. And today, AI is in the high end, is crossing a few tens of thousands of accelerator, HPC networks, national labs, and so are even larger than this. And what we've done with Ultra Ethernet is that we leveraged this vast experience that we have, and we went all the way to 1 million endpoints. Another lesson the industry has learned and is applicable to both cases is the concept of multipathing. Everybody here may remember the early Internet days with spanning tree, one path, and so on. It is very common today in the industry to understand that multipathing allows good return on investment, as many AI applications are deployed in a claw or fat tree network non-blocking, and leveraging all of those paths is going to give me the best job completion time. Another thing that both applications can benefit from is the concept of relaxed ordering. With relaxed ordering, what we mean is that originally MPI, Rocky as another example, were using strict ordering. Here is the request coming down from the application, and exactly that order must be followed on the network. However, AI applications that typically like training is really leveraging the network for very large messages. Inference has a little bit different patterns, but whenever it is possible, it would be nice to look into what the application really requires. And if I'm about to move 1 megabyte or 1 gigabyte across, what I really care for is the last part of that message safely arriving to the other side. I don't really need all packets to travel like a train in a set of cars. And so relaxed ordering is really useful. However, anytime I'm using multipathing and relaxed ordering together, I run the risk of stuff arriving out of order. We are talking about packet spraying. So each packet is going to pick the path that seems to be most available at that point in time. So we have optimized load balancing that is coupled with that multipathing based on the most recent congestion information. That obviously raises the question of what happens when a packet arrives out of order on the other end. And the answer, the Ultra Ethernet answer for this is that this is done without a reorder buffer, and we will touch more about that again. Congestion is obviously not desired, and if you have perfect orchestration, which is easier with systolic workloads, your chances of congestion are going to be reduced. However, some traffic patterns and some lack of perfect synchronization is going to cause congestion. And in some cases, people also deploy environments that are not fully provisioned end-to-end with the same bandwidth, so you have oversubscription. In those cases, you really want to have congestion that is not only fast to react. If you think about the duration of a congestion event on 800 gig network, sometimes it is shorter than one round trip time. So you really need to modernize your congestion so it's going to become easy to use, not brittle, not too many knobs to turn. At the same time, allows you to start at full rate and actually react very fast, even if the event is short-lived. Another important message is about that what people think of an ergodic tie between the RDMA and the transport that carries it. What is really needed is optimized RDMA. The RDMA has its own benefits as its kernel bypass and no CPU involved, therefore much lower latency. But the minute you untie it from the transport and you provide those services that I mentioned here, you get a much better result. So if we look at the bottom here, everything else is self-explanatory, and in interest of time, I'll move faster. We are really looking for environment that couples something not easily done of high utilization as well as low tail latency. Why are we interested in low tail latency? Obviously, this is about parallel processing, again, both for AI and HPC. And if Johnny is late to the party, nobody else can raise a toast. So you want the tail latency to be as controlled as possible. On the upper left hand, what you see is really the box we are operating in. So application layer is unchanged, the Ethernet is unchanged as well, and everything else in the middle is what we are trying to do. In this slide, I'm going to give you a quick tour of all the key features that we are doing in Ultra Ethernet Consortium from the top to the bottom. Mind you that we are going to release our first spec 1.0 later in Q4, but if you go to our website, ultraethernet.org, you could download over there a white paper as well as a blog, and we are working on another blog that should be released literally in the next few days. That is going to give you even more depth than what the time I have here today allows. But let's take a look from the top and going down. Mentioned that the goal here is to keep the APIs unchanged, so you could actually take existing AI or HPC workload and move them to run on top of Ultra Ethernet once products are going to be there. The transport, which is representing the bulk of the work and the innovation here, allows you to do the multipathing, the packet spraying, without requiring a reorder buffer. However, if you want to have a reorder buffer, this is supported as well. Reorder buffer has its own limitations as it doesn't scale nicely with bandwidth delay product, but this option is available as well. The ROD, Reliable Order Delivery, is a service we offer so that anyone who has an application, sometime it could be an HPC application, sometime it could be for other reasons that somebody has already written an application such that it is dependent on ordered. So that gives you, if you want, backwards compatibility. However, we also offer the reliable unordered, and that actually corresponds to the comments I made 5 minutes ago, where you could actually spray on all the available links that are not congested, and the message actually goes zero copy, direct data placement, and when the last piece arrives, the application would get notified. Hyperscalers typically in the last so many years prefer to run on best effort network. However, they didn't really like PFC, as this was causing congestion, sprawling, and other issues. So that is the main mode that we support today. However, for other use cases where people are accustomed to lossless, that mode is available as well. On congestion, as I described earlier, some of the challenges and the opportunities, we have enhanced transport or sender-based type of congestion control, allows you to start full bore, very easy ability to detect what of your path is congested and then avoid that for one cycle. It is really relying on two things. It relies on the ECN that all standards data center switches support today, as you could see on the network layer. And then it measures the latency. So it can handle also and take into its computation sender-based congestion as well as receiver-based congestion and adapt accordingly. On top of that, we also have a receiver-based. The industry has seen, starting from 2018, all sorts of papers, SIGCOM and other events where people were proposing receiver-based. In this case, the receiver-based is going to dole out credit for all the potentially competing flows, and therefore, after one RTT, would really avoid any incast or other congestion you have closer to the receiver. Another feature that we are supporting is the idea of trimming, which really means that a busy switch that is about to drop a packet instead would send just the header on higher priority to ensure that the signal about incipient congestion is really arriving to the sender, and the sender could react faster. This is optional on the switches, but would be supported by all endpoints. And the last one on that list, which, trust me, is just a quick shorthand of all the things that are happening in the transport, is the idea of switch offload in network collective that for all reduce through a few other scenarios is really beneficial, can allow you to get the network to 2x of what it can normally do. A few optional features at the data link. LLDP enhanced in order to communicate all those optional features. Link level retry, if you look at an accelerator that has 10 terabits going to 20 terabits divided by 400, 800, whatever speed you want to look at, signaling speed that is today 100 going to 200, you'll find that you have extremely large number of links. Any transient power issue, other reasons why your link is going to start stuttering really affects everybody, as we discussed on the idea of the tail latency. However, instead of retransmitting from the software, as was the case so many years back, or even from the transport, which potentially is partially or completely in hardware, here we transport directly from the MAC layer, which really means you buffer the packet, you wait for acknowledge from your partner, and then if you didn't receive it, you immediately retransmit. So that would be your speediest way to get all the information arriving at the same time, not slowing down everybody. Another way to help you tail latency. And for HPC and other applications, we have compressed header, which is going to help those applications that are extremely latency sensitive. Today, we only support 100 gig, as IEEE was not done with its 200. The minute 200 shows up, we'll have that supported as well. And last comment on this busy slide is that in order to further allow products optimization, we offer different profiles for AI and HPC. As an example, the relaxed RDMA support is more applicable to AI. HPC many times would like to get everything. In interest of time, we'll skip these two slides as you will get them in your handouts, and this slide is a summary of all the different key features and their advantage on the right side. Multipathing is going to give you higher network utilization. Flexible ordering, similar, would allow you to move all of the information, leveraging all of the different paths available. We discussed the congestion and the switch offload, the advantages of the simplified RDMA. Security, which is very important to us, was integrated, thought together with all the transport and other features at the same time, make it actually optional feature, but easily integrated. It's not an afterthought as was happening with previous generations. Where do we stand in terms of timeline? Some of our work groups have advanced to the point where we are doing legal review right now, and so their work is going to be released soon. Even the key transport parts of the overall spec are beyond technical freezing. Some of them are getting there later this month. And so we expect this to be publicly available later this year, as well as those vendors who have worked with the consortium long enough are busy preparing products that potentially hit the market next year. And I'll stop here. I think that's pretty much the time I have. See if there are any questions.
Great. Thank you very much, Yuri. There is a question in the Slack, which I will relay. On slide 6, on congestion control and lossless, if you have receiver-based scheduling and latency measurement, why is ECN needed for lossless congestion control, or are they orthogonal?
Yeah, let me go back here. Yeah, so the ECN is actually used. Let's start with the normal way it is used. Sender-based, I need to get a signal of congestion that is starting or is already happening or is about to die down. And smart use of ECN coupled with the latency allows us to actually kind of detect when congestion is starting, when we are in congestion, when congestion is decreasing. Technically, with as the person who asked the question was mentioning, when you're using receiver-based, you don't really need anything. However, in the very extensive simulation work that members of the consortium have created, you want to deal also with the first round trip time. You want to start by getting very good, fair, and optimized load balancing. So you want to have some indication of whether you have congestion. If your network is really provisioned correctly, if your orchestration, let's take AI as an example, is done and everything is scheduled nicely, yes, the chances are not going to be very high, but reality shows that even in those scenarios, you do have transient congestion. So the receiver-based also leverages that information of if there are hotspots in order to avoid them and optimally use load balancing. Hopefully that was the answer to that person's question.
Yeah, so there is more activity on Slack. We're not going to be
Okay.
able to do all the questions on Slack. So Yuri, you might want to take a peek at the Slack channel later.
Sure.
I will relay one last question here. Just going to take them in order in which they came in. Tushar Wakarkar asks, can UEC be adopted for the scale-up network as well?
As I mentioned on one of the previous slides, maybe one of the first slides, there were discussions at Ultra Ethernet in the early days, what network we should be targeting, as potentially many of the people who attend today are aware. There are other efforts in the industry right now around scale up. So the question always is not only what is possible, but where, what direction the industry is going after. And so Ultra Ethernet at this point is really, and it's in release 1.0, we are really releasing technology that is best optimized for scale out, but everybody knows Ethernet, and Ethernet has been in all sorts of different applications, and future will tell where Ethernet is going to end up.
Okay, great. Well, thank you very much. And again, there are other questions in the Slack channel.
Sure.
But I'm going to leave those to you to answer because we are running a bit behind, and I know there is awards and what have you. Hello, Artem. I'm going to hand it over to Artem. Thank you very much, Yuri.
Thank you.